Today we're going to take a closer look at buckling. As you know, buckling is a failure mode that occurs when a member is subjected to gradually increasing axial compressive load that causes the column to deflect laterally. This is the Euler buckling equation. It will be helping us predict how much force will make a member finally buckle. Some factors to consider when trying to predict how much force is required to make a member finally buckle are the length of the member, the area of inertia, and the modulus elasticity. In addition to knowing how the variables in the Euler buckling equation relate, we also know a couple other factors about buckling that will help us determine how different members buckle under force. If much of the material is placed away from the axis, then the member resists buckling effectively and the moment of inertia is high. Contrarily, if all the material is concentrated close to the axis, then the resistance to buckling is very poor and the moment of inertia is very low. Today we are going to see how three different wood members, each 2 feet in length, all with near identical cross-section areas, resist buckling when a force is applied. The first member we will be testing is a rectangular cross-sectional member with an area of 0.047 inches. This member has the majority of its material close to the axis. The next member we will be testing is a square cross-sectional member with the same cross-sectional area measurement as the rectangular cross-section. Because they have the same cross-sectional areas, are both 2 feet in length, and are made from the same material, the main variable between these two members is their cross-sectional shape. The square cross-section has less of its material close to its axis than the rectangular cross-section member. The final member we will be testing is a circular cross-sectional member. Its cross-section area is only 0.002 inches greater than the other two members, but shares the same length of material. The circular cross-sectional member has the least amount of material at the axis. Based on what we know about the factors that play into buckling, we can predict the following. The circular cross-section piece will resist buckling the most. This prediction is based on our knowledge that most of the cross-sectional area in this member is the farthest away from the axis. We know based on Euler's buckling formula that this would mean that the moment of inertia in this member will be high once a force is applied, and that the buckling will be resisted effectively due to the parallel relationship between the moment of inertia and critical force. We can also predict the opposite. The rectangular cross-section piece will resist buckling the least. This prediction is based on our knowledge that most of the cross-sectional area is nearest to the axis. We know based on Euler's buckling equation that this would lead to the rectangular cross-section member to have a low moment of inertia and will not be able to resist buckling effectively at the same force that we believe the circular cross-section area could. We also think that the square cross-sectional area will buckle less than the rectangular cross-sectional member, but more than the circular cross-sectional member. The first member we will test will be the rectangular cross-section member. As you can see here, the rectangular cross-section buckles very easily. The next member we will test will be the square cross-section member. I'm going to apply roughly the same amount of force with my hand to the member, and if our predictions are correct, the member will not buckle quite as easily. So I'll continue to apply more and more pressure until the member buckles similar to the first.
This is the 3/16 by 1/4 inch.
So far, our predictions have been correct. We will next test the circular cross-section member. As you'll see in the video, I'll have to apply much more pressure than I did to the first two to get this circular member to buckle. According to the Euler equation, if the effective length is decreased, the amount of force to cause the column to buckle will increase. In this next step of our experiment, we will demonstrate how all the necessary force to cause buckling will increase. Cross-sectional shape still determines the amount of force to cause the column to buckle.
With the addition of this floor system is to demonstrate how it affects the buckling of the column. This is the 3/16 by 1/4 inch with the floor system. See that?
Mm-hmm.
Go ahead.
All right, this is the 1/4 inch diameter, and it takes a significant amount of weight to make it bend.
As you can see, although that lateral bracing increased the amount of force necessary for the columns to buckle, the cross-sectional area also played a role in how much force was needed for them to buckle. From this experiment, we can conclude the following. The cross-sectional shape of a member does impact how a member reacts to a buckling force. Members with their area farther away from their axis are able to resist buckling more effectively than members whose area is concentrated closer to their axis. Column members with a higher area moment of inertia can withstand a greater amount of force before buckling.